Hello, everyone. Today's talk, we will have Andreas Hülsing, who is a professor at Eindhoven University of Technology, and will be presenting his work on post-quantum PAKE and quantum accessible ideal ciphers. And please welcome Andreas, and you can start, please.
Yeah, thank you for having me. I will start with a topic that is a bit further away from the topic of the seminar, I think, and then I will go to something that's a bit closer to it. Namely, I will start talking about PAKE, password-authenticated key exchange, and then I will hopefully convince you that we need quantum accessible ideal ciphers to prove at least some of the proposals and where the challenges are. And if you want, you can interrupt me at any point and ask questions. I think this should be fine. So this is joint work with a bunch of people, Catherine, Yushuan, Mike, Varun, Sylvia, and Obi. Some of the slides are actually stolen from previous talks from Sylvia and Yushuan, and from a bunch of different affiliations. Yes. So I will start talking about PAKE. Then I will introduce a specific version called CAKE that was proposed, I think something like 3 or 4 years ago. Then I will talk about an ideal cipher simulator, and finally I will come to another work that goes towards building such a simulator called Feistel-based. Okay, let's start with the PAKE. So, I mean, this is kind of crypto 101, but right, if you do general password authentication, there's this issue that you can have a server that does a man in the middle and just asks for the password and then mirrors this password to the next party. This is, of course, not the only problem with password-based authentication, but password reuse and things like this are really a very common issue. Like you don't even have to do a man in the middle. You can just pose as a server. And one way out is something called PAKE, where you actually do not ever send a password, but use the password to authenticate a key exchange. Right? So you build a general authenticated key exchange protocol, and somehow, if both parties share the same password, so I'm only talking about symmetric PAKE here, then they get the same shared key in the end, and otherwise they will either abort or will get just some different key. And this is something that's actually used quite extensively in practice. So for example, symmetric PAKE is used on your passport. So when you're traveling and you're using these automatic entry gates, then you have actually a contactless communication between your passport and the machine. And this contactless communication is secured by a PAKE. So the machine will read the machine readable part of your passport, you know, this part on the bottom of your passport, and we'll use this as a password to secure the communication so that people like listening in couldn't learn, for example, your picture or your personal data. And also in more recent Wi-Fi standards, actually, a PAKE is used. And there's a bunch more, but I think these are the most popular applications. Right? So what do we need in terms of security of a PAKE? Obviously, we need kind of the standard authenticated key exchange security. So this is key indistinguishability. So at the end, the key that comes out should look random to anyone that isn't one of the two parties. Then we have two additional properties, and these are linked to the problem that passwords have to be considered low entropy, right? Of course, people can pick highly secure passwords, but in general, we have to assume that users use somewhat low entropy passwords, which means the password space can actually exhaustively be searched quite efficiently. And that means we must never, ever give the attacker an offline oracle, right? If from, for example, listening in on the communication, the attacker gets something that allows them to test the password guess offline, then you're in trouble because it can just search the password space and will eventually get the correct password. And similarly, if you have an active attacker, we only want to give that attacker a single password guess per active attack. So any active attack should only allow it to validate one password guess and not 2, 3, or more. So that we can actually rate limit an attack by just rate limit the amount of login attempts that we actually give. And there is actually a pretty straightforward blueprint how to build PAKE. This is from the 90s and it's called encrypted key exchange. And the idea is that you just use a block cipher to encrypt the messages of an authenticated of a key exchange, and you encrypt this with the password as a key. Right? And this is indeed something that, for example, is also used in your passwords. In some variant, but essentially that's it. Okay. So given this, let's look at what happens if we want to make this post-quantum and why this actually needs reprogramming twice for strange reasons. So if we want to do this post-quantum, then what would be nice is if we could do this with a CAM-based key exchange, right? And this is what proposal by, I will not read the French names, but a bunch of people from France actually does, called CAKE. It takes EKE and does it with a CAM. And so I'm not sure if you can see my mouse. We start just by doing key generation, then we encrypt the public key under essentially the password. Bob then decrypts, gets the public key, does an encapsulation, and sends the ciphertext again encrypted under the password. And you can actually do the same thing with only one ideal cipher instead of two, but then you have to add an additional authentication tag, which demonstrates to Alice that Bob actually knows the password, right? So instead of encrypting C, it will just send an authentication tag along, which includes the password, the key, and all the information from the transcript, essentially. And this one is called OCake. And there are security proofs for both protocols in the original paper in the UC model, and then there were tight game-based proofs in the Bellaro-Roggeway paper model. One was done by Pan and Seng for CAKE, and we started working on the same thing in parallel, but we only noticed the other paper. Well, it only appeared online when it was accepted for AsiaCrypt, and then we put ours online within a few days. But yeah, it was not yet in submission, so we ended up at some smaller conference where we did this for OCake. And all these proofs essentially have to make 3 assumptions on the CAM. The first one is that it's in CPA, so this gives you that in the end the key looks actually random. And then we have 2 more properties. Maybe let's start with the uniform public keys. So any bit string of a given length should look like a public key. This is something that you need so that you can program or can put public keys into the ideal-cipher, and you can interpret ideal-cipher outputs. It's public keys, so this prevents something where the attacker just decrypts the public key, like the encrypted public key, under all possible passwords and throws away like 90% of the outcomes because it's clearly not a public key under your CAM. So each of the outcomes actually has to look like a valid public key to the attacker. And then there's another property, which is called anonymity under plain text checking attacks. And anonymity means that you cannot link a ciphertext to a public key, right? And I will come to why this is necessary in a second. Maybe as a note, all these proofs are actually in the classical ideal-cipher and random oracle model. So they need both. Okay, so why do these proofs need anonymity? Well, the issue is that if someone was able to link the second method, the second message to the first, this would again give you some password checking oracle. All right, so if you assume that anonymity was broken, so let's take a stupid, or not stupid, but let's take a setting where the CAM just attaches a public key identifier to the ciphertext for whatever reason. All right, this means that you can just enumerate the password space. So you decrypt, you will get a pair of public key, of candidate public key and candidate ciphertext, and only if the ciphertext matches the public key. So if the public key identifier in the ciphertext matches the public key that you obtained, this is a potential valid candidate, and otherwise it's not, right? And given that the password space is far smaller than the space covered by the ideal cipher, and the ciphertexts and plain texts should look more or less randomly distributed, this will only happen for random public keys and ciphertexts with negligible probability. So you can actually bound this. And this gives you an easy distinguishing attack. So I think you will probably need something like 2 or 3 attempts, and you can filter out all the passwords except the correct password. Because for that one, it will actually work, right? Okay, so this means that somehow our proof or our reduction has to deal with such an anonymity attacker, which means that for the case that an attacker follows this strategy, some property, some security assumption has to be violated. And obviously, like the straightforward thing is, well, this violates anonymity of the CAM. So let's build a reduction to this. All right. And if you want to do this, the anonymity game works as follows. You get a pair of public keys and you get a ciphertext generated under one of them, and you have to decide if it's under the one public key or the other. So if you want to use this in a reduction, you actually have to make sure that the EPK that you get when you decrypt it under the correct password gives you one of these challenge public keys. All right, and then in the game hop, you would replace this challenge public key with the other challenge public key, and so you actually encrypt under a public key that was never sent in the encryption, eventually thereby making the second message independent of the first. And this is something that we can actually show formally using something called a meta-reduction. So we build a reduction or meta-reduction that takes any reduction for PAKE, any security reduction, and it will use it to actually solve anonymity in case that it doesn't program. Right, and this is actually the most technical part of the paper that we wrote, but I will not go into the details. I will just tell you what we actually prove. So with this meta reduction, we are able to show a bunch of necessary conditions for an ideal cipher simulator that can be used to actually prove this secure. And so what we show is that any reduction which proves cake or O-cake secure in this game-based BPR model against a potentially quantum adversary has to program the ideal cipher to place the anonymity challenge. All right? And this is something that generalizes to any bijection. So if you do something like recent proposals, use a 2-round Feistel network instead of an ideal cipher, and then program by using implementing the Feistel with random oracles. This is possible, but then you need this programming. And this also generalizes to UC security, because for the special case of UC security, any game-based proof, any UC proof actually implies a game-based proof for the case of PAKE. I did not have the time to look up the paper, but this was proven quite some time ago. There's one limitation. We know that you can circumvent this issue if you don't have just computational anonymity, but statistical anonymity. So if you have statistical anonymity, you don't have to give a reduction, and therefore you don't have this issue that you have to place a challenge. However, our case actually includes all the FO transformed camps like Hyper or HQC. So this is actually exactly the class for which we use as a counterexample in the meta reduction. Okay, I'm going quite fast, so feel free to interrupt. So far we have the necessary conditions, but what about sufficient conditions? We actually also showed, and I will not bother you with how we do this, but we give a security proof using an ideal cipher simulator, which has the following two properties. So if you have a simulator that simulates encryption and decryption, given a challenge set X, which has this following two properties. First, it's indistinguishable from an actual ideal cipher. And second, if an attacker, when interacting with the ideal cipher, outputs an element from the domain of the ideal cipher, so essentially an encryption on the ideal cipher, when it's interacting with the simulator, it will output an element in the image of the encryption using the correct password applied to the challenge set. So phrased differently, when you're interacting with the simulator, the attacker will output an encryption of a challenge under the session, like the target password. All right? And these properties have to hold probabilistically, but in the asymptotic setting, obviously, the indistinguishability has to hold with overwhelming probability, and also the success probability of placing a challenge has to hold with overwhelming probability. Otherwise, you don't get a security proof, because both terms actually pop up in the final bound. And again, we can of course extend this to general bijections, but then the statement gets a bit more complicated. And classically, we can actually instantiate this, which is pretty straightforward. For reasons you want to introduce a key derivation, which is random oracle based. So you take the SSID and a password and first feed it into a random oracle, and then you encrypt on the resulting key. And then you have an ideal cipher that is lazy sampled, programmed with the challenges. So essentially you're programming a challenge on any decryption query that uses the correct password. And And so either you have a multi-instance notion of anonymity, then you have sufficiently many public keys to do this, or if you only have two public keys, you would just guess which one is the key query. Then you have to prove four things. First, you have to bound the key collisions. So this is a random oracle argument. Then you have to bound the probability of forward ideal cipher collisions. So these are two queries to the encryption procedure using different passwords, which result in the same encrypted public key. Why is this a problem? Because if you were able to find such collisions, you could actually test more than one password at a time using an active attack, right? Because if you send such a query and then you follow the protocol and in the end it fails, then you know that neither of these two passwords was the correct one. Then you have to bound the lazy sampling aborts. So this is, in this case, lazy sampling means I'm sampling and I just abort the moment I actually have a repetition, because then I don't have a permutation anymore. So this is just about indistinguishability. And finally, I have to bound the probability that the output that A sends was actually produced by a forward query. And this is the case because if this happens, we have to assume the attacker correctly guessed the password, and we cannot program anymore because they would detect it, right? Because they would decrypt and then under the corresponding secret key, whatever ciphertext you send back, and they would notice that something is wrong. So what if we look at quantum?
Andreas, can I ask one question?
Sure.
On the previous slide, so where does the simulator comes up here? Like,
So the lazy sampled program part, that is the simulation.
okay.
So we simulate, like, I mean, an ideal cipher in the sense of a family of random permutations, we simulate by actually lazy sampling the input-output pairs, right? So whenever there's an encryption query, we sample a random output, and vice versa for a decryption query, except if this is a repetition, so query that was made before.
Okay, so yeah, so basically by simulator you mean a lazy sampling plus a reprogrammable version of the ideal cipher, right? That's
So in this case, you're not reprogramming, but for certain queries, you do not sample the outcome, but you actually take it from your challenge list.
yeah. Okay.
Yeah.
Okay, thanks.
Thanks for the question. And this is actually the part which quantumly doesn't work anymore, right? Because in the quantum setting, I don't have single dedicated classical queries on which I can react, but I can have superposition queries. So I actually have to have some form of initial permutation family fixed, and then, well, if we look at the QROM, we can actually program later. We can replace parts about which the adversary does not have sufficient information yet, right? So that we're only queried with low amplitude. But we don't have anything like this so far for an ideal cipher. We did actually not even have a quantum ideal cipher simulator that's efficient until very recently. And also for the proof steps, so this collision bound, this is a random oracle bound. We know how to do this. But especially for the second and the last point, these talk about the direction of a query, right? And so if we look at something like, if we assume we would have something like a compressed oracle version of ideal cipher, so there is a proposal by Unruh which essentially does this. So it it also builds the database and essentially measures out any kind of collision, thereby keeping the partial view of the function a permutation or consistent with the permutation. This is unable to actually record in which direction a query was made. Right? And finally, we cannot really bound this lazy sampling awards because they don't really happen.
So, sorry, again, so this is under the assumption that your direction bit is also in superposition, or direction can be classical here? The direction of the ideal cipher query.
If the direction would be classical.
I mean, then it should be easy, right? Because then I can record. So
no, because the problem is I'm using a joint database, and in this database, if I start storing the direction, I think so. The intuition, and I talked to some people about this, is that this actually will be impossible.
okay, because so I was thinking about this. So if I don't, so there is this work where like the adaptive query pattern, you can replace it with a static version where like you just make a few more queries. I think so. If you have, let's say here, two oracles, you will make two q many queries instead of q queries, and then you can embed an adversary who is making adaptive query pattern in a static query pattern. So in a way, like the query pattern, it's known at the start itself. So whether you will make a forward query or a backward query at the ith index is already known at the start. So I'm just thinking like if the direction is classical, then this should be doable or no?
If you can maybe let's discuss this at the end.
Yeah.
I would be very interested in this. We searched a lot and didn't find anything, but maybe we really just missed this. And of course, I should say, right, this is the classical approach to the whole thing, right? It doesn't mean that this is impossible. It's just saying the classical way to prove this is at least tricky, if not impossible, right now. So I can say we have found some tricks to deal with some of them using what comes in a moment. Because this assumes actually that we have some way to simulate a quantum ideal cipher. And for the rest of the talk, I actually want to talk about one way to do this. So maybe let's take a step back, because this work was not only motivated by this. I started looking into quantum ideal ciphers, I think 2014, discussing this with people. But this was always kind of a side project, and I never found the time to really work on this in detail, but it somehow didn't move, right? So when the compressed oracle came, we had virtually anything you could wish for in the Q room. Like these techniques developed extremely fast, and we now can do most of the stuff we can do classically somehow also in the quantum setting. For quantum random permutations, there were several attempts to actually generalize this, and they were all flawed or were lacking a proof in the end, until somewhat recently. So there were dedicated domain solutions, let's say, that started popping up. So we had some form of query recording coming in 2024. We had some reprogramming forms. For example, you can now do measure and reprogram for ideal ciphers. There was a lifting paper in 2025. And there's actually some adaptive reprogramming tools that were developed by Chris Mayans and others. Those we missed because they called them quantum or point resampling lemmas, which is indeed what happens in the proof, but it's not what it's used for. And so maybe I'm not the only one that missed this. At least I think all from our team missed this. Yeah, but so this progress only happened somewhat recently, and it's kind of domain-based, right? So you have a solution for query recording, you have a different solution for measure and reprogram, you have yet another solution for adaptive reprogramming. So the obvious question is, if we look at the class at the random oracle setting, we have this one tool called the compressed oracle technique, which enables all these techniques. Don't we have something similar in the permutation setting so that we can just generically lift all these QROM tools to the permutation setting? And this is where we came up with this idea of the Feistel tools. This actually was inspired by one of the papers of Chris and others. I think they had a construction which, following our naming convention, would probably be called FP2F. Right? So 2-round Feistel, a random permutation, and then another round of Feistel. And we instead looked at a sandwiched Feistel construction. So you have a random permutation left and right, and then you have a 3-round Feistel network in the middle. And these outside permutations are there to actually hide the structure and make it look random and hide anything that's going on inside. And the inside part is what makes it useful and allows to actually lift existing QROM techniques to the permutation setting. Right? So this is at least the idea. And in the paper where we introduced this, we looked at 3 techniques. So first is adaptive reprogramming technique from 2021, I think. Then we looked at query recording following Mark Sentry's work. And finally, we looked at measure and reprogram. I should mention, before I will explain the query recording, how it works intuitively, there is a concurrent work by Carolan where he proves that Unruh's simulator actually is indistinguishable from a random permutation. So it's a valid simulator. This was an open question posed by Unruh, I think, in AsiaCrypt 2023. And Carolan uses exactly this, what we call P3FQ, as a vehicle in the proof. So this is not the construction that he uses as a simulator, but something that he uses to prove that Unruh's construction is actually indistinguishable from a random permutation. This thing has one disadvantage, and that is that you get a quite significant tightness loss, right? So you can actually do anything, and Unruh's simulator has this advantage that it's essentially a single compressed oracle that you're dealing with. So everything should lift, in theory, more or less trivially. But you're gaining this, well, n to the 12, or square root n to the 12, 12th root of n penalty in the tightness. Okay, that being said, how do we do query recording as one example? And this is just an example of how to see how we extend the techniques, and that it's not entirely trivial. So what we do is, as you might expect, we use compressed oracles for the different random oracles in here, so H1, H2, H3, which means we have independent databases for these three. Right? So over the queries, we are recording the queries, but this means what we're actually recording are the x1, y1, x2, y2, and x3, y3, and not capital X and capital Y, which are the inputs and outputs to the permutation. So following the compressed oracle technique, what we want is in the end that we actually can look in the database and see what queries were made to the construction. Right? And here we get an actual issue, which is the potential over recordings. So in the end, we check which are the linked entries in our databases, right? We only have the databases of the hash functions. So we're looking for the triples x1, x2, x3, such that x1, x or the hash entry of x2 equals x3. And then for those, we can easily directly compute x and y because we have q and p available, and we can get the wires entirely from this. The problem is this equation x1, x or h2 of x2 equals x3 can have collisions. And so if I have two different x1, x2, which leads to the same output, I will actually have two x3 likely in there. So I will actually have 4 combinations instead of 2, right? So this means I will have 2 false entries in my database. And I can actually even have x1, x2 that were caused by different queries that give me yet another x3 in there. So in general, this can pollute our database. As these are somewhat random pollutions, it shouldn't harm the bounds too much. But most of the bounds that you get are just talking about the number of entries in your database, so you get a loss from this, right? We started trying to bound the collision probability for this. It turns out this is actually not as easy as we thought. So this gets easier to analyze if you shift one of the permutations in. So if you have this 2 Feistel permutation, 1 Feistel construction, then we can get a tight bound. But as it is, we did not manage yet to get a tight bound on this. Okay. So this gives us a tool to simulate ideal ciphers, or actually ideal permutations, but you should be able to generalize this to ideal ciphers. So where's the issue if we look at the simulator from before? The problem are exactly these directional query things. So this is the part that we did not solve. Right? We can deal with the simulation and we can do the programming in theory. We don't do lazy sampling anymore, so we don't have to bound this. We need an additional bound for the programming. But this is something we know how to do because this essentially comes down to a measure and reprogram. But the problem is that we don't have a way so far to deal with this directional queries. And at this point, I'm already at open questions. So we are working on follow-up, but in general, I think the question is, what kind of stuff can we lift with this P3 of Q? Especially, is there anything that we cannot lift? So far, it seems that everything works out fine. But maybe there's something where it actually gets stuck. You do definitely sometimes gain a bit of a tightness loss. Another thing are applications. So we did look in the original paper at duplex sponge version of here Chamir and analyzed this. And for the query recording, we looked at the double-sided zero search problem, which is kind of the main problem people looked at so far. But of course, there should be more stuff where you need actually quantum accessible ideal ciphers or quantum accessible random permutations. And finally, really something that still bugs me is how you implement the simulator, or actually how we can analyze the simulator. That's it from my side. Thanks for staying around, and I'm happy to answer questions.
Thank you, Andreas, for this interesting talk. I know probably Ashwin has some questions, but maybe we can start with others first if you have any questions. If you have questions, please either ask directly or like write them in the chat. Okay, I guess Ashwin, you can discuss while people think about what to ask.
Yeah, so I think a different question is about the Feistel tools, because that is something quite interesting for symmetric key provable security. And I guess, I mean, this is something that does not come up much for public key analysis, is the concrete security that you can get with this tool. So as you said, like, because there is this over recording phenomena here, right? So you, if you have Q entries in the database, you get Q square many choices right now. So do you see a way to improve this by, let's say, increasing the number of Feistel rounds in the middle, right? Instead of 3 rounds, if I have more rounds, can we somehow, maybe not, but I'm just.
No, as I said, like by moving the permutation in, this allowed to analyze this more tightly. And I have to admit, I don't know from the back of my head where the issue was that we were unable to bound the probability distribution in the third database. I think that the question was if the attacker can intentionally make forwards and backwards queries. So, and I think we just failed to make to formulate this argument which says the adversary's queries are uniformly distributed, right? Because like if we can argue that the adversary's queries in the Feistel network are uniformly distributed, which they should be because they go through 2 random permutations at the beginning and the end, then it's just the probability of like just a statistical probability of a collision occurring, right? But we somehow did not manage to make this argument formal. So this was somehow what got us stuck. And this is right. And this is why if you move the permutation like in one step, you get this argument kind of for free, because it means that whatever you did before, the outcome will be just a random x3 value.
Okay, but I mean, yeah, then in that case, why not just add one permutation in front of P or Q, let's say, and then get a tighter bound? Because as I see it, it doesn't really matter if you, as long as the number of functions that you use is polynomial in terms of efficiency, right? You don't lose anything. So
logically not, but I mean, of course, you need another round of simulation. Then the question is how you simulate. So the initial idea that we had was, well, you can just, if you assume AES or so as a good quantum assessor random permutation, right? A pseudo random permutation, then you can just use this to simulate, right? Or any other block cipher kind of. But actually, I think Yushuan and Barun came up with a conditionless simulation. But that happened during my parental leave, so I don't know the details about that one.
Okay, maybe yeah, we can discuss this
Yeah.
a bit later because there is another question, I think, from.
Yeah, so question from Shan Chen. Thanks for the nice talk. Are there many real-world protocols that really need QRPM, QICM for a PQ proof? Could you give some examples? Sorry if you mentioned this before.
So indeed, this is kind of a thing that we are also currently struggling with. There are symmetric key constructions, of course, where this becomes interesting. For certain tools, they only really appear if you have public key primitives. So something like adaptive reprogramming, where you're programming based on a classical query. That is something that typically then appears in a protocol that uses a symmetric primitive, right? And the main tool that we found so far was this DFSF, this duplex sponge Feistel construction, which is something that they advertised as the signal, thinking about like using this, and it turns out they kind of use something like this, but they faked it, and they are not using a duplex sponge, but something else. And but they are considering to actually move to that if it's better understood. My original motivation, so my background is in hash-based signatures, right? And my original motivation started when we presented Sphinx. There were Eike kills and Mark Fischlin sitting in the back and afterwards saying like, yeah, this is all nice, but then how you do actually prove security of the hash function that you're using, right? And this was when I was really starting to look into, okay, how can we argue about the security of our hash function constructions? And so I think this is one other important application, like how can we reason about the security of sponges in a quantum setting? And how can we reason about the security of block cipher-based hash function constructions?
I think there is a paper also, I don't know the details, but about the study of ASCON in the quantum world, like the ASCON AED. And so there might be a connection there as well.
Yeah, actually, so just to add, I think, Andreas, your reprogramming tool was really useful in symmetric key for post-quantum security, like constructions where you have access to the internal primitive. So ASCON,
Okay.
as Mustafa mentioned, is one example. We had a paper, me and Ritam, with others, on Feistel, key alternating Feistel. So we use it there. And then, of course, there is the Ibn Mansour papers.
I have to admit, those I did not follow. Yeah, I learned the later in your career it gets, the less time you get for reading. That's,
Yeah. No, so actually, that's not a way you would approach these problems in the classical setting. Like in the same construction, if you analyze in the classical setting, we would never think of reprogramming as a tool. But in the quantum setting, because of all the quantumness, like reprogramming came naturally, and yeah, then that tool was really interesting for us.
Yeah, it's really funny because you have to think about a lot of stuff. So also if you want to, I did quite some work on getting bounds for specific hash function properties, right? Even in the random oracle model, like classically, you're just doing counting arguments, more or less. And quantum, this all becomes reductions actually to established hard problems, right? Or, and this is how they first analyzed the double-sided zero search, you end up with something that really uses full quantum query complexity methods to analyze the problem at hand. But this means you have to learn these methods, which are quite painful to understand in my experience. So I think the polynomial method and also the adversary method, somehow they are intuitively easy, but the moment you want to apply them yourself, especially to something which is not a Boolean function problem, this tends to get quite nasty.
Yeah, they're kind of restricted as well. Like when you consider adaptive adversaries, it's a bit hard to, because the conditions there are really restricted, right? You need very strong statistical properties to apply those results.
No.
From the limited experience I had with trying to use them, so.
Yeah, and they're usually targeted at worst case bounds. So
Yeah.
you have to to find a way to make them give you average case bounds. Yeah.
Okay, so I guess
Okay.
that's.
Any other questions? Ashwin, also, if you have more to add.
So I have a few, but I guess I can discuss them offline as well after we stop recording, because I
Okay,
think
if
that's something.
anyone has any other questions, you can ask them now. Otherwise, we can also stop the recording and see.
Yeah,
But
and
yeah,
just
let's thank the speaker for this interesting talk. And
Yeah, thanks a
thank
lot,
you,
Andreas.
Andreas,
Yeah.
for giving the time during this talk. And
thanks for having me.